Hi Calculus 3 students. This is the fourth video on the series lectures, on the power series lectures. And we're doing yet another example. And this one will be much more complicated. We will see that we will hit like a big bone somewhere along the lines. And we will need more theory to solve it. So, otherwise, for what values of x is this convergent? Remember, for now we have the ratio and root test that can help us with this. And what decides what we use is almost just do we have factorials or not. That being said, even if you don't have factorials, the ratio test will work. It might give you something more tedious than the root test, but it will still work. In this case, let's use the root test. So root test, remember, we're doing the limit as n is approaching infinity of the nth root of the absolute value of an. Okay. Now, this limit will disregard this factor, okay, because the absolute value of -1 to the power of n is actually simply equal to 1, right? So whenever you throw in the absolute value, if this series is alternating, it won't matter. So this is the limit as n is approaching infinity of the nth root. So remember, I disregard this factor. So what do I have? I will have the absolute value of x plus 2 to the power of n divided by, and these are all positive numbers, right? 5 to the power of n, square root of n plus 1. So let's actually make the root slightly bigger. You have 5 to the power of n, square root of n plus 1. Okay, now the first thing I want you to notice is that if you look at the exponents, right, you have like an nth root over here that you can distribute over all the factors. It's going to cancel this, it's going to cancel this, but as it distributes over here, like notice that this is to the power of 1/2. Okay, so you divide that by n further, and it means that this factor right here will be to the power of 1/2n. So okay, let's get these two factors out of the way. We have the limit as n is approaching infinity of the absolute value of x plus 2 divided by 5. Now, what does that limit look like? It looks like n plus 1 to the power of 1/2n. Remember, the n here is due to this root that we distribute over, and we multiply the corresponding roots. Okay. So now let's have a look at this limit. Okay, I just want to split the calculation a little bit. I will do it in red, let's say. Let's focus on this because this is actually not obvious. So we take the limit as n is approaching infinity of n plus 1 to the power of 1/2n. Okay, if you replace n by infinity here, you will get infinity. But if you replace n by infinity here, you will get 1/infinity, which is 0. Infinity to the power of 0. Remember that this is an indeterminate power. How do you solve for that? You will take the limit of the logarithm. So limit as n is approaching infinity of, and whenever you take the logarithm of this, okay, you know right away that this is an exponent will be brought up in front. That's actually the purpose of doing it. So actually, let's call this limit L. Let's call this limit, I don't know how to call it actually. Let's call it L. I don't mind, or just like script L like this. Yeah, L will be the limit as n is approaching infinity of 1/2n times the ln of n plus 1. Now, if you replace infinity, you're going to get simply infinity divided by infinity. So in this scenario, you know that you can use L'Hopital's rule. So L'Hopital's rule tells you that this is going to be the limit as n is approaching infinity. What's the derivative of 2n? Simply 1. No worries there. And what's the derivative of ln of n plus 1? That's going to be 1 over n plus 1. Clean up. You get the limit as n is approaching infinity of 1 over n plus 1, so 0. Okay. However, be careful because that's not the actual limit. It's the limit of the logarithm, right? So this is just the limit of the logarithm. So to get the actual limit, the limit that's right over here, you have to take e to the power of 0. So let's write that down again. Okay, so we have limit as n is approaching infinity of n plus 1 to the power of 1 over 2n. So now that's going to be equal to e to the power of l, which means e to the power of 0, which is 1. Okay, so far so good. So we saw that this limit is 1. Okay, that's a good news. Let's continue over here. It means that this limit will give us finally absolute value of x plus 2 divided by 5 times 1. 1 due to all of this calculation that we have done at the bottom. So what can we conclude from there? Now let's erase this. We know that the root test, we're going to have a convergent result if this big limit is smaller than 1. So this series converges if the limit that's over here, so absolute value of x plus 2 over 5, is smaller than 1, which means absolute value of x plus 2 is smaller than 5. Okay? We also know from the second case of the root test that the series will diverge if this is greater than 1. So this series diverges if the absolute value of x plus 2 divided by 5 is actually greater than 1. So in this case, x plus 2 will be greater than 5. Okay, so we do know some stuff. Okay, we know that this series converges if, now have a careful look at this. It means that x plus 2 is going to be between 5 and negative 5. That's what the absolute value means, right? So it means that x will be between negative 7 and 3. So this is when the series converges. We also know that this series diverges if x is below negative 7 or x is above 3. So converges here, diverges here and here. We need to investigate two more values, okay? So what if x is equal to negative 7 or x is equal to 3, right? What's happening at exactly these two values? Well, here we have a problem because if x is equal to negative 7 or 3, we have that x plus 2 divided by 5 over 1 like x plus 2 divided by 5 is exactly equal to 1, okay? Which means that by the root test, it gives an inconclusive result. So the root test gives an inconclusive result. What does it mean? It means that at these two values of x, we have to use another test of convergence. So in the next video, what I'm going to do is I'm going to present these tests of convergence. We're going to just state them all, and then we're going to finish that problem. Okay? So we need to use another test of convergence. But the good news is that we have to do so only for these two values. For these two values. See you in the next video.